Why can't you just define the area of where it sticks just a little bigger, so then that becomes true?
Because it's a physical property of the material. If the metals are too close to each other for the things that stick to them to happily coexist, then they're not going to happily coexist. It's not a property I can mess with. All right, 3. Adsorption at one site only. Single type of site. So if I have a catalyst surface, are there multiple binding modes? Are there multiple sites available to adsorbate? Yes, this neglects that. Yeah.
If you were binding like acetylene,
The ethylene.
An ethylene rather, and it used 2 sites, would you just have the number of available sites? Okay.
That's fine. And that does not violate these assumptions. You can bind to more than one site with a single adsorbent, but the sites have to be, quote, the same type. In other words, there's nothing in my sticking coefficient, there's nothing that allows me to have multiple sticking coefficients which change depending on which site it's binding to. It's just one. Yeah.
So would you, if you were doing ethylene, would you have to have a reaction where it changes from just the pi bonding to the double sigma if it diffuses and then just picks up a second site?
If I'm modeling ethylene adsorption and I'm using this pure Langmuir model, I'm going to be in bad shape because it's actually going to shift from di-sigma from this mode to the pi bonding at higher coverages. And at that point, things break down. But just about every case, that's true.
Okay.
So the reason why this works is because of a fortuitous cancellation of errors. And because a lot of the things that we're discussing can impact the rate of adsorption, but not enough to really undermine this basic idea. So despite all of these assumptions, this Langmuir model works really well. Desorption is, so far we just talked about rate of adsorption, right? We drew it as a double-sided arrow. So let's look at what is the rate of desorption. And at first we're just going to write down the rate. We're going to ignore K, and then we'll talk about perhaps where K comes from. I see how he has it defined, kind of a cop-out, but we'll talk about it. It's actually how you do it. So the rate of desorption is what? K for, desorption, we'll put that there, times what? Some concentration. What's the concentration? So the K for desorption I can also write as equal to the K for adsorption divided by big K for adsorption, but the equilibrium constant for that process, right? So this is nothing more than K -1 is equal to K1 over big K1, which you guys have seen that before. It's nothing more than that. Just now that it's dealing with adsorption and desorption, just changes where we get this rate constant from. So at equilibrium, let's talk about this guy. What is true? The rate of adsorption is equal to 0, and I'll just remind you that this is now a net rate. What is that rate?
That's K times the times A times J times the star.
Minus.
Minus K.
So this is adsorption, K desorption
Of A star.
times concentration of A star. We can plug in what we know, and so we get K adsorption times the pressure of A, the concentration of vacancies, minus the concentration of adsorbed species divided by the equilibrium constant for adsorption. So all I've done here is take these equations and write them now in terms of concentrations and pressures, and that's what we get.
Real quick, is that big K that you just erased ADS and then,
Yeah, it's the equilibrium constant.
okay.
I'll leave that last bit up. So, I realize I probably erased that too quickly. So at equilibrium, the net rate of adsorption is equal to 0, which is equal to all that stuff. So if that all is equal to 0, then again, at equilibrium, what is the concentration of my active species? How do I solve that? Yeah, I just set this all equal to 0. This constant goes away, right? And it just is rearranging that. And what you get is big K of adsorption times the pressure times the concentration of the vacancies. To rearrange that, you get the equilibrium constant is equal to concentration of adsorbed species divided by concentration of vacancies, pressure A. This should look oddly familiar. I know that this is a pressure term, but let's squint and imagine that that's a gas phase concentration. A star over star over A. That's it, right? The only difference is that we've changed the gas phase concentration into a pressure and we put the RT that shows up when we do that into the rate constant for adsorption. This is essentially something you should be kind of inherently familiar with. If I have A plus star goes to A star, the equilibrium constant is products over reactants. And that has not changed. So the final concentration as a function of pressure and this is for molecular adsorption, and we're going to talk about what I mean by that in a second. I don't mean physisorption. You can use this for physisorption as long as you neglect all of the things that physisorption can do, like make multilayers. You can still use this for physisorption, it works. It's just for adsorption. But by molecular, I mean something a little bit different.
How did you get this equation again?
I'm taking the concentration that we have and relating it back to essentially where you have, did I erase it? Yeah.
Oh, related to CV.
Yeah, and so CV is CT divided by 1 plus the amount that's on the surface. The amount of A on the surface. All right, so there's another type of adsorption. So imagine I have hydrogen and I have a metal surface. Does hydrogen chemisorb?
No, not dihydrogen.
not as dihydrogen. What happens if I expose a metal surface to hydrogen at room temperature?
If it's an alkaline metal, you're going to have a problem.
Yeah, well, yeah. It'll dissociate. And so this does adsorb, it chemisorbs as 2 hydrogen atoms. So this is called molecular adsorption, what we just talked about. And we went from A plus a site goes to A star. What if now we have a system where we have A, this is dissociative adsorption. So A plus 2 star goes to B star plus C star. And I'll put this in the Fogler notation as well. Yeah.
So what causes the bond to break?
Dissociative adsorption, you have to understand, is made up. Dissociative species can still physisorb, but certain things react so readily upon contact with a catalyst that it makes more sense to combine 2 events, physisorption and dissociation. Now that's one theory. The other theory is that certain species cannot physisorb. As soon as they collide with a surface, they break apart. So from that theory, this is a distinct process from adsorbing and then dissociating. But it's not clear for very many systems whether or not this is nothing more than physisorption followed by chemisorption. So what causes it to react? The same reason anything causes itself to react. There's a catalytically active surface. In this case, it is able to break the hydrogen-hydrogen bond, and it's typically favorable to form 2 hydrogen metal bonds instead of keeping that hydrogen-hydrogen bond intact. There's a barrier, but the barrier for this dissociative adsorption processes is so small that often